Does AIA Philadelphia award continuing education units for these sessions?
Yes.
Okay.
So
you guys have got all of that back in paperwork, credit award, all that stuff taken care of?
Yeah, most of these we get health, safety, welfare credits for.
Okay.
And if people registered, we'll have it'll all go straight through the AIA. And we just have to like note them as signed in, but we'll ask people to drop their member number in the chat in case they didn't register and they're joining late.
Have you guys been through the 2030 DDX yet?
The new one that just came out?
Yeah.
You've been through the new one, David?
Oh, not the new one. I haven't seen the.
I've been trying to get my hands on it for a couple of weeks.
Well, and new one, old one. You've been through the 2030 DDX in terms of goal setting.
And as a group,
oh,
yeah. So our first, actually, this is helpful for you to see. Well, I've got it up. Our first few sessions really focused on that. So session 2 in January, we did a review of sort of the DDX as a whole. Session 1 really focused on what the requirements are for 2030 signatories. And then we dug into how to report interior lighting or interior only projects, and then projects as a whole right before the typical reporting period ends. It was extended this year, but go ahead.
Did you use the DDX, or when you were talking about the DDX, did you use it in terms of talking about benchmarking and goal setting?
Oh yeah. Yeah, we had a range of different project types, from hospitals to labs to mixed use. When we did the reporting help desk, that was our breakout session, was to, take these typologies and walk people through the process of establishing those projects in the DDX, looking at their baselines, looking at their target EUIs based upon the goal setting of the 2030.
Okay. I've got a few slides in talking about benchmarking and goal setting, because I think that's really important as part of the process of getting the energy simulation work kind of framed, and this is what our goals are, and so forth. And so I'll run through those really quickly because you guys have already been through and seen most of that anyway.
But I think it's, we have new people constantly joining these meetings, and I think it's great to reinforce those and contextualize the conversation around it, energy modeling.
Yeah, and I'm not going to be talking about the DDX as a reporting tool or any of that stuff. So it's more using the research part of the DDX to look at what a goal might be associated with a project.
Yeah, I think that's great to go through and to emphasize. Hey everyone, thanks for joining us tonight. We're really excited for our 8th session of the 2030 Working Group. We've got Kim Shin joining us and Tony Esposito from TLC Engineering. And as you join, please remember to drop your name, email, and if you'd like credit for this session and did not register, your AIA member number into the chat. So that we can make sure that you get credit for attendance. So you can just drop those in the chat, your name, email, and AIA member number. while we're waiting for folks to continue joining us. So again, if you're just joining, drop your name, email, and AIA member number in the chat, and we're going to get started. So this is our 8th session of the 2030 Working Group, which started in December of last year. And we're really excited to have Kim Shin and Tony Esposito from TLC Engineering join us tonight to talk about demystifying energy modeling and to answer a lot of questions that have been raised over the course of the development of the 2030 Working Group. A couple sessions ago, we talked about the integrated design process, and this was a slide we showed showing the conventional design team structure versus an integrated design team structure. And one of these bubbles includes building design and simulation specialists as part of the integrated design team. And I think the way that we think about this as a process is something we're going to dig into more deeply tonight. And it's going to be a really great in-depth understanding of what this process looks like throughout design phases. And during our last session, we had a really great presentation from the folks at Kieran Timberlake about the way that they've integrated the 2030 commitment into practice. And I think we'll see a lot of the discussion tonight building off of that conversation from our last session. And with that, I'm going to hand it over to Kim. And just as a reminder, if you're just joining us, please drop your name, email, and AIA member number into the chat so we can make sure that you get CEU credit. Kim, I'm going to hand the screen over to you.
Great. Thank you very much, Bunny. For those of you who don't know me, my name's Kim Shin, and I gave myself this title, Sustainability Wizard at TLC Engineering Solutions. My role within our firm is really with the sustainability and high performance building team, acting as a internal and external consultants to our design teams as they embark on high performance projects. As Bunny mentioned, I'm also joined today by some folks from our Philadelphia office. Tony Esposito is the managing partner for our Philadelphia office, and we're also joined by Siobhan Powers and Michael Walkino. Siobhan and Michael are mechanical engineers and energy modelers there in our Philadelphia office. So even though I'm coming to you live from my office above my garage in Nashville, we've got TLC people on the ground there in Philadelphia. So tonight we're going to be really focusing on how to incorporate energy modeling into the design process, specifically focusing on how to integrate the building specialist, the simulation performance specialist into the design, talk about what it is that architects need to work with those energy modelers and building performance simulators, talk about how and when to do energy modeling and how it can impact the design, and then actually talk a little bit about what are the financial benefits of doing energy modeling. So I want you to know that the AIA has done a really great job of establishing a lot of very valuable, very helpful resources that are at your fingertips as members of the AIA and interested members of the architecture community. I think one of the really greatest things that the AIA has done in the past couple of years is decide to move high performance design out of its silo and push it into the mainstream of architecture. So that when we talk about design excellence in architecture, that we think about energy performance and indoor environmental quality and placemaking as much in our design award programs as we do about the beauty of the project. So if you haven't been to these pages yet, please do. You'll be getting copies of these slides, so you don't need to copy down all these fancy URLs. They'll be embedded in the PDF that you can get of these slides. But just know that they're out there, and we're going to be referencing some of those. So one of the most important things that we can do, and I'm sure this was discussed in the IDP session, is you need to know where you're going with your project. And in the same way that it's really commonplace for us to say, okay, this is a school building, it's got 42 classrooms, it's supposed to be built for $17 million, it's located in Chester County, and it has to be done by next May. We can also set those same sort of goals within our energy performance vocabulary for the project team. And the deal here is, if you don't know where you're going, you just might end up someplace else. And I'm so happy that we're going to have baseball this year, maybe a little bit of it, but I'm excited that I can quote from my favorite philosopher about goal setting. So there's any number of different places where you can go to establish what are really important pieces of information to give to your design team. And two of those are the 2030 DDX. This group went through the DDX way back early in the year before the world changed. I'm going to come back to it a little bit and really talk about how to use it as a benchmarking and goal setting tool. And then also Energy Star Target Finder, which is actually sort of embedded within the DDX, but can actually be a separate tool that you can work with. And once again, going back to the AIA's own words, you really need to take the time to develop what these benchmarks and goals are going to be for your project and share them with the team. Because if the team doesn't know in really quantitative numbers where this project is trying to get to, your likelihood of getting there is really suspect. So the 2030 DDX has this screen, which is the input screen, where you can basically set your project up, where you go to what kind of project it is and roughly how big it is. And really the only three pieces of information that you need to start this process is, where's the project located, not its address, it's even its zip code, its area code. What kind of project is it? Is it an office building? Is it a school? Is it a hospital? Is it a warehouse? Is it a retail establishment? And then finally, roughly how big it is. Is it 1,000 square feet, 10,000 square feet, 100,000 square feet, 1,000,000 square feet? You don't need a set of floor plans or elevations or even a site plan to start doing your simulations, because those three pieces of information tell you climate, they tell you program, and they tell you relatively how important the internal loads are versus the envelope loads. The smaller a project tends to be dominated by its envelope loads. The larger projects tend to be dominated by their internal loads. With those three pieces of information, you can really start to generate information that's valuable. So for this particular project type, its baseline, its average of all buildings of this type located in this area is going to be 90,000 BTUs per square foot per year. The 2030 challenge goal, that 80% reduction that we're under right now, sets that goal as 18,000 kBTU per square foot per year. So this is a really very quick way for you to just put in that basic sketch type information, not even before sketches, of being able to decide where you want to go with the project. Now, in this particular case, I had selected the IECC 2015. There in Philly, you're under the 2018, but this will actually tell you, if you design to code, what your savings are going to be. But we don't want to design to code. We want to do better than code. Another really valuable piece of the DDX is the research tab. And there are almost 50,000 projects that have been entered into the DDX, and it's really pretty easy to slice and dice them by project type and location so that you can establish sort of what the best of the best projects are doing. So if a project's gotten into the DDX, that means that somebody cared enough to do that, and it's probably a pretty good project. So what you see here on the screen is a scatter plot of medium-sized office buildings in climate zone 3A, and lets you see on the vertical axis what the predicted annual energy use intensity is versus the project size across the horizontal axis. So that can help you determine what sort of the peer projects have been doing in that connection. So one of the really cool things is if you hover your cursor over one of those dots, you can actually get a little bit more information about that particular project. But remember, the DDX is making these projects anonymous, and the projects that your firm has entered actually appear as a different color dot, and whether they've been modeled or simply done to meet the energy code. So without going into intricate detail, this is a really great way to benchmark what's been done in projects of that type and location, and help you make a really intelligent decision about what the project that you're designing might use as a goal. Energy Star is another tool. This is the URL to get there, and then for reasons that I have never quite understood, you actually have to click on another link within that page to get to the portfolio manager. Once again, you enter some really simple information. Where is the project located? How big is it? And then the project types are in a pull-down menu. You can then enter your design target. So for this particular example, we're using an Energy Star score of 75, and then with using, just as I said, how big's the building, where's it located, what kind of building is it, you get to see some information about what that would be in terms of designing to an energy use target. So in this particular instance, the Energy Star Portfolio Manager gives you a design target of about 40,000 kBTU per square foot per year in order to design that building to be in that 75th percentile of performance of similar buildings. And there's even some more detailed information about this. And one of the things that I find really interesting about using this tool is if you look at the energy cost associated with this building, about $20,750 a year versus a median property, sort of the average of properties of almost $30,000 a year, you can see that designing to be that much better than the median property is going to save the owner a couple $1,000s a year. So you can, even without doing an energy model, begin to start to put a fence around what kind of energy operating savings that this sort of approach can yield. So if you'd set a Energy Star target of say 90 and driven that site EUI down to say maybe 20 kBTUs per square foot per year, then you could actually have some energy cost associated with your local market that will help you define what it is that the owner would see in terms of operating savings. And this is even before you have a design. So get it out of your heads that you can't do an energy model, that you can't predict energy use, that you can't do any of this until you've got a design to model. You're actually using this sort of benchmarking and goal setting information to set the stage for going into modeling. So one of the things that we want you to do is to think about different sets of goals. So one of the things that LEED and the 2030 Challenge has really kind of gotten into our heads is using annual energy use as the metric that we design to. So we call that energy use intensity, or EUI, and that's that 18 kBTU per square foot per year. And you get LEED points for that, and you get Energy Star ratings for that, and you get your 2030 achievement for that. But something that's really kind of gotten glazed over in all of that discussions that's really important and is one of the key takeaways for you today is doing things to decrease your peak loads. So what did I do here? I changed my screen. There we go. So that annual energy use is actually a surrogate for operating costs. And that helps you make decisions over the life cycle of the building. But we find that owners are generally a lot more interested in first cost than they are in lifetime operating cost. And the thing that is the surrogate for first cost are those peak loads. So peak loads are used to size systems and equipment. This is where we decide, 40 tons, 1 million BTUs, ducts that are this big are basically sized off of those peak loads. So those peak loads are driven by owner decisions, mostly having to do with the program, what's going on inside the building, and architecture decisions, massing, orientation, and envelope. Now, we mechanical and electrical designers are really good at calculating peak loads, but owners and architects make the decisions about how big those loads are going to be. I cannot emphasize this enough, that looking to your mechanical and electrical designers to help you reduce the first cost, you are looking in the wrong place. Look in the mirror. Your architecture and owner decisions are driving the first costs of these projects. And if you can start to do models and calculations that show the impact of those decisions on first cost really early in design, you can really move the needle. Now, one of the real bonuses is that when you get smaller mechanical and electrical systems, they generally use less energy. So this is the holy grail that we're looking for, is reduced first cost and reduced annual operating costs for lowest lifetime cost. And those first costs getting smaller will get your owners to buy into this idea of high performance buildings. The money that they save in decreasing the size of the equipment, they can spend on other things like marble in the lobbies, or higher efficient equipment, or prettier colors, or whatever it is that you architects decide is really important. But making the system smaller is, once again, a decision that is made by the architect and the owner generally working together. So when you go to set goals associated with the peak loads, I plead with you to look at the envelope and to set goals associated with the envelope. Where, and here's your mechanical engineering lesson for the night. This is an equation that you can take away from you. The conduction heat load is equal to the conductivity times the area of the envelope times the temperature difference between the inside and the outside, the delta T. So what you're trying to do here is look for opportunities to reduce that U times A. You're not going to do much to change the delta T because your building's where it's going to be, and climate is going to dictate the delta T. But that U times A is completely within your decision-making field as an architect. So what you're looking for first is for components that have very high U times A results. So in the example that I've given, the U times A for the roof is about 390. The U times A for the opaque wall area is less than 450. The U times A for the window area, and remember, this window area is pretty small, is almost 1,400. 3 times as much as the other two components. So what does that tell you? Look for opportunities to shrink that U times A. And where are the opportunities? It's where the big pieces are. So reduce either the area of those components with high U values, or reduce the U value of those components that have very large areas. So as you're setting your goals, you don't only set a goal of, I only want 18,000 kb2 per square foot per year, but I want my area weighted U value to be 25% or 30% or 50% less than the code maximum allowed. So that's a really easy calculation for you to do going in, is look at your building area, look at what you think your surface area is going to be, assign some window areas, and calculate what that code maximum allowable U area weighted value will be, and then set a goal for you as an architect to bring that building envelope number in at some percentage better than that code maximum allowed. I can't tell you how many times I've been brought in as an energy modeling consultant by an architect who says, I want a whole lot more glass on my building and I need you to trick the code into letting me do it. If I didn't need the money so much, I'd just turn around and walk out when I get that. But that's not where you want to be. I want you to be looking for a goal for you to design the envelope to meet. So one of the big ones with this is window to wall ratio. And study after study has shown that window to wall ratios above 40% provide no additional benefit for daylighting, but they will cause significantly higher conditioning loads. A window to wall ratio between 30 and 40% sets the stage for both good daylighting and energy performing. And this quote is straight from our friends at the AIA. limiting the window to wall ratio may feel like a design constriction for project teams. However, the way designers leverage constraints to their advantage is one of the key considerations of the framework for design excellence, celebrating both beauty and performance. Now, this little graph down on the left-hand side is probably a little bit hard for you to read, but when you get the copies of the slides, you'll see that for different window to wall ratios, we generally see the minimum for annual energy performance to be in that 30 to 40% window to wall ratio. Any greater than that, your loads get too high. Any less than that, you don't really get good daylighting harvesting opportunities. Also, in most commercial buildings, the lighting power is a major component of both peak loads and annual operating loads. So you need to look for opportunities to reduce those lighting power densities. So once again, what you want to do is look and set a goal to give to your lighting designer and your electrical engineer that says no more than X% of what's allowed by code. Don't let them design up to the code maximum. Give them a goal at something less than that. And then as we decrease the energy associated with the envelope and the lighting, we find that the next big opportunity is plug loads. And this is another opportunity for you to work with your owner. And many times we've done projects where the owner has said, I need to be able to handle 10 watts per square foot plug load. Where did that come from? Well, I had one of my interns go out into the area that we're talking about designing a building for, and I had him turn over all the stuff that was plugged into the walls and write down the nameplate information and gathered up all of the maximum power draw was for that. And I added it all together and it came up to 10 watts per square foot. And time again, we have gone back and said, wait a minute, not all that stuff is going to be on at the same time, and none of it is going to be pulling that maximum load all at the same time. Let us figure out what you're really using in that space. And invariably, it is maybe even as much as an order of magnitude lower than what that adding up the nameplate exercise got us. So instead of 10 watts a square foot, it's actually closer to 1 watt a square foot or even less. So if you don't do that and you size the systems for 10 watts a square foot, you have oversized the mechanical electrical systems and spent way too much money on them. And besides that, they don't operate very well when the load is that low. So take the time to figure out what the real load is on your plug load systems. So here's some list of do's that come right from the AIA. Number one, you want to build iterative energy modeling into your project design budget. Doing one energy model is good. It's better than doing no energy models, but the more you do, the more you can use that information to help shape your design. So budget the time and the fee into the project process. And we'll talk about where those points are within the process in just a second. Model early. As I said, you can start doing simulations and models and getting information about energy use and peak loads before you even have a cocktail napkin sketch. In fact, having that information might actually make your cocktail napkin sketching more productive. So take the time to do that research before the guys with the felt tip pens go nuts in the back room with the bum wad. You want to give them some information to help them inform that process. Think about the energy model as a cost control measure. Once again, this idea of keeping the peak loads under control is a cost control opportunity. Once again, reduce that first cost, make those owners and program managers happy. If you can't afford an energy model, at least manage the window to wall ratio and lighting power densities. Those are simple calculations that are pretty good proxies for energy models on really small projects. And realize that most of a building's energy use is generally tied to the building's function. And the bigger the building gets, the more this is the case. The less the envelope becomes a part of the equation, the more is what's going on inside the building. And the better information that you can gather on what's going on inside the building, the better you're going to be able to predict the actual energy use of that building. And resist the temptation to say, oh, you know, the last one I did at 10 watts a square foot plug load and 2 watts a square foot lighting and a 0.25 U value on the envelope. Resist that temptation. Look specifically at your building and set aggressive energy goals for the design team. This is a tremendous resource. It's the Architect's Guide to Building Performance, and it is free. Your dues, and thank you dues paying members of the AIA, have paid for this really valuable resource. And it's all about how to integrate performance simulation, energy modeling, daylight analysis, computational fluid dynamics into the design process. So there's the URL for finding the thing. It guides you through how to use the information that you get out of these simulations and helping you make design decisions. It introduces and talks about something really important, the Ashrae Standard 209, and we'll talk about that in a little more detail in just a second, as a framework for helping your team manage the energy modeling process. It talks about some questions and approaches that you might pose as an architect to your building simulation consultant to help you make those design decisions and provide some case studies and practical application of those. And I was privileged enough to work with a lot of great architects and other engineers in helping the AIA put this document together. So I don't get any royalties from it, but it would make me feel really good if you either downloaded a copy for free or paid for it at the AIA bookstore. So graphically, this is a really good representation of what building simulation does and folds into the process of delivering a project. From before you have the contract in the RFQ, RFP stage, all the way into occupancy. Now, the top half of this graphic is really about what we call single aspect simulations. And massing and orientation, solar shading, daylight and glare, envelope and facade, thermal comfort studies. These tend to be really, as the name indicates, single aspect situations and relatively easy to do and are things that a lot of architects have the skills and the tools to be able to do. And we'll talk about those in a little bit more detail, but suffice it to say that the information that comes out of those things, as seen in this diagram, really needs to happen in conceptual and schematic and early design development. To look at different options and how different design decisions can move the needle in these single aspect simulations. The bottom half of this graphic is whole building energy simulation. And one of the things that's really interesting about buildings is they're almost organic. almost biological in the way that many different systems interact with each other. How the lungs and the heart and the brain and the digestive system and the muscular and skeletal and skin all work together and give each other feedback and influence each other in different ways, so that buildings are exceedingly complicated in their physical interaction between these different systems and components. These simulations tend to be very, very complicated. And the software that's used to do them is extremely powerful. And I like to tell people that energy modeling and daylight simulation and computational fluid dynamics, when they all work together, is a very powerful tool. And like any powerful tool in the hands of someone who doesn't know how to use it, you can be killed or maimed. So don't think just because you can buy a piece of software or download it free off of the internet and read a tutorial that you can start plugging in numbers and get things that make sense. You really need to understand the physics of building science in order to know whether or not you're getting good stuff out of this. So we tend to think of the top half of this graphic as being the domain of architects and the bottom half of this graphic as being the domain of professional building performance simulation consultants. So I'm often asked by architects, hey, can I just do this for myself? And I say, I can spend time training you, I can work to help you understand what's going on, but if you go off and do this stuff behind my back, don't call me if one of your junior architects loses an arm inside one of these simulations. It's gonna happen. Go ahead and get us on the team. Let us help you work through this. We're not gonna spend a whole lot of your money right away. So once again, this is the kind of stuff that really lends itself to what architects are doing in the early design phases, tying out different massing, orientation, fenestration patterns, glazing selections, shading details. Those sorts of things can really be done very quickly. And typical software that you would use to do this are what I like to call the zoo, the rhinos, the grasshoppers, the honeybees, the crocodiles, the rhinoceros. You know, the entire animal kingdom now is able to bring to bear multiple parametric analysis to look at these things. But don't confuse those with rigorous or robust energy modeling. So what happens here? Well, this is essentially an integrated iterative process where architects pose specific questions, provide some inputs to a simulation. The building simulation consultant runs the simulation, provides some interpretation, works with the architect to make decisions based on those results, and then goes back and iterates on that again. So it's really important that the architect learn to ask the right questions. You can really inform and lead the design process by asking relevant questions, not relevant, but relevant questions. You need to provide information about what you want us to evaluate: shading, envelope properties, geometry, occupancy schedules, things like that. You need to be involved in the process so that you know what's going on in going into the model. Once again, models are pretty dumb machines. If you put garbage into them, you're going to get garbage out of them. So you need to work with your energy and building performance simulation consultant, helping them understand what it is that you want modeled. And then using that information to actually make your design decisions. So here's a typical direction from an architect. Run the energy model. Well, why? What do you want to find out? Do you want to know what the largest energy uses are? Do you want to know which of these massing options is preferable energy-wise? Do you want to know if you're even meeting code? What's the relative importance of 5 different variables? Is window to wall ratio more important than lighting power density? Is roof insulation more important than an occupancy schedule? You need to find out what's driving the energy use. And then, something as practical as will this shading system pay for itself? Or do a daylight analysis. Well, what do you want to know? Do you want to know daylight autonomy? Do you want to know space, annual solar exposure? Is it a glare problem? Will we be able to do without lights most of the year? What is it that you want to find out? So don't just say, run me an energy model. Tell us why you want the energy model, what information it is that you want to discover from the energy model. And that will really help us tailor and focus what we do. Run an energy model is in a direction to a building performance simulation is analogous to walking into a restaurant. I know many of you haven't done that and you might have forgotten what it's like to do that, but back in the day when you would walk into a restaurant, just sit down and the waiter comes up and you say, bring me food. Well, what kind of food? We got a menu of selections here. No, food, I want food. Do you want a lot of food? Do you want a little food? Do you want food in different portions? No, I just want food. Well, you're going to pay a hell of a lot for me to just bring you a table full of food. If you had told me more focused that you wanted a salad and a half a cup of soup, I would have given you a salad and a half a cup of soup. It would have been a great salad and a half a cup of soup, and it would have cost you 1/100th of the table full of food that I had to bring you. So think about what you're asking for before you get your building performance guy burning a lot of time and money. To that end, there is a group of architects out on the left coast and also a few up in Boston who have created something called Project Stasio, the standard simulation inputs and outputs. And this is basically a tool, a crowdsourced tool to help architects develop targeted questions. So this screenshot from the Project Stasio website is actually the questions menu that you can go into, and there are questions to ask about annual energy use and peak loads and daylighting and whether or not the beef stew will give you heartburn or not. There are a really great set of questions for you to start looking at, to maybe help you not maybe take that question verbatim, but to help phrase that question on your project. So this is a tremendous resource, and it's the more people like you get involved in asking questions and contributing to it, the more robust it will come. It's also an incredible resource for us as building simulation experts because it helps us help you define what those questions are. It's also a really great resource for graphical reporting on energy models. Because unfortunately, most of us building performance simulation, we're numbers folks. We love tables and matrix and we can see the numbers when we look at them, but we need to be able to turn those numbers into graphics that owners and architects can quickly understand and help them make decisions. If we give you, the output of an energy model is reams of paper with numbers in a tiny little font. If we give that to you, you're just going to recycle it. This is helping us come up with a better vocabulary to deliver results to you in a graphic format. So I told you I was going to tell you about Standard 209. So the good news about Standard 209 is it's available from Ashrae. The bad news and the good news is it's a really small publication. It's this thick. It's 20 pages. Unfortunately, there are no pictures. You know, you leave engineers by themselves, you're not going to get very good pictures. And it's not free. It's going to cost you $94 if you buy it in PDF, or $136 if you want a printed edition along with the PDF. Full disclosure, I don't get any royalties from this, but I also helped write this one. The idea here is that this standard is not telling you how to do an energy model, but it does tell you how to use an energy model during design. And it is a perfect companion to the architect's building performance simulation guide. So we've got the architect's AIA document and Ashrae 209 working in tandem together. It is a minimum compliance standard. It is not a collection of best practices. There's a whole lot more that you can do with an energy model than what's in the standard. But what it does is sets a common understanding of what energy modeling is. So if you want to follow the standard, you must establish an energy performance goal. You got to know where you're going. You need to conduct an energy charrette. You need to get the people who are involved in the project, who have a stake in the energy performance, get together early on and talk about those energy goals and how they're going to get there. You need to do a climate and site analysis. Once again, even before you have a concept of a site plan or a floor plan or a set of elevations, you need to do a climate and site analysis. You need to have someone who's experienced in building energy modeling performance and energy simulations, who's got a background in building science and energy modeling to either do or supervise the modeling. And then you need to be performing those energy models during design. And you need to do at least 2 energy models during the design phase. One of those 2, you can do more than that, but you must do at least 2. And one of those 2 must be done before you leave schematic design and specifically focused on reducing the peak loads on the building. Stop me if you heard me say reduce the peak loads. This is becoming more and more important to us as we develop the idea of delivering affordable high-performance buildings. So going back to the Architect's Guide to Building Performance, those first 3 energy models that happen back in the RFP, RFQ, schematic design, conceptual design phase are the most important models you can run. And it goes back to the McClamey curve. You know, you've seen the curve that says early in design, the effort to make a design decision is very low. The value that it adds to the project is very high. As the project timeline moves along, the later you are in the project, the more expensive it is to make a design decision and the less value that it has for the project. So those early energy models, the ones that you do during schematic design, will have the most profound effect on the performance of the building, and they will be the least expensive energy models. If you wait to do an energy model until after the design is done, you are closing the barn doors after all the cows have gotten out. If you find out that your building is not meeting your energy goals after you finish design, what do you got to do? You got to redo design. You got to spend your own money. You're not going to convince the owner to pay you more money to go back and change the stuff that you should have gotten right in the first place if you had been doing energy modeling all along to help you guide your design decisions. By the way, here's an important point, that as designed energy performance model that's defined in Standard 209 does not count as one of the 2 models that you must perform in order to be in compliance with the standard. It's all about doing modeling during design. So that load reduction model is the one model that you must do that has the greatest impact on the energy performance of your building. So Ashrae Standard 209 was created basically for 3 big reasons. One, for organizations like the U.S. Green Building Council that certify high performance buildings. If you go to LEED version 4.1 and look in the integrated design process credit, you will find that they make reference to Standard 209, that you should follow Standard 209 in the early phases of the integrated design process. Number 2, there are utilities and agencies that will pay you to do energy modeling. And heretofore, there's been sort of this squishy sort of thing where those people were not really sure that they were getting their money's worth. So if you follow Standard 209, you can be pretty assured that you're getting a consistent product that then the utilities and agencies can use to justify those expenditures to produce low energy buildings on their grid. And then finally, this is a way for building owners and architects to have a uniform way to specify a scope of work for building energy modeling. Free to you as an attendant at this webinar, you will get a copy of a scope of work document for acquiring building performance simulation services within the Standard 209 framework. This is a Word document that you will be free to edit. It's meant to be an attachment to or an appendix to an RFP or an RFQ that defines scope of work and services for building performance consultants. So we really hope that you will take that and incorporate it into your next RFP or RFQ when you're soliciting energy modeling services. So I'm going to take you really quickly through the first 3 modeling cycles in Standard 209. The first is called simple box modeling. It happens during conceptual design, and it establishes an estimate of the annual energy and peak heating and cooling loads. It is HVAC system agnostic. It doesn't matter what your HVAC system is. It's before you even have an HVAC system. It's just, there's one there. You want to look at building geometry, window to waste wall ratio, and shading, and the thermal performance of the envelope. You want to do this before the geometry and orientation get finalized. You want to do it before or even during the charrette that is a mandatory feature of Standard 209. At TLC, we do what we call the Energy Wizard Show, Wizard Hat, where we go into a charrette and we'll run dozens of energy simulations live with the project team during the charrette, give you results real time, help you make decisions going forward about what you're going to do in conceptual design. And as a part of Standard 209, we even include an appendix that tells you how to do simple box modeling. This is the one part of the standard where we actually tell you, here's how to do that modeling. The idea here is to get a representation of how big's that building, where's it located, what kind of building it is, where that energy is going to be used. So in this particular instance, that tells us that that 51% slice of the energy use of this building is where we need to concentrate our efforts. It really gives us information about how to and where to concentrate our efforts. If it turns out that internal load is not an important thing to do, but the envelope is, or vice versa, it really helps us focus our efforts as we go forward. So the second is what we call conceptual design modeling. This is where we start to look at different forms, where a lot of times architects will produce 3, 4, maybe a dozen different forms before they settle on one. And we can do analysis of those forms to provide information that will once again define building annual energy use and those peak heating and cooling loads, and be HVAC system agnostic, and then prepare comparative analysis of those. Once again, it won't tell you which of those dozen different forms to choose, but it will give you information about the relative energy impacts of those forms. And then finally, cycle 3, the mandatory cycle, is we're looking at that selected massing and then looking at peak load reduction strategies, where we want to look at least 3 peak load reduction strategies selected from the envelope, lighting, internal equipment, outdoor air, and passive conditioning or natural ventilation. And then use our energy model to really evaluate each one of those load reduction strategies as compared to the baseline. Once again, using identical HVAC system types. What we've described here in the first 3 modeling cycles, no real mechanical or electrical design has been done, but it's a really good idea to have those folks in the room to help inform some of those decisions. So we talked about, let's make a financial case for doing energy modeling. So a colleague from HOK, Annika Landreneau, some of you may know Annika, she's in HOK's Washington, D.C. office, and I got together and did a presentation at the 2017 AIA National Conference in Orlando. What Annika did was went into HOK's portfolio and looked at projects where they had done energy modeling and looked at how much money they spent on energy modeling, and then the energy cost savings that resulted from those modeling efforts. And you can see that in most cases, almost all cases, the simple payback for those modeling fees was less than 6 months. In the first year of operation, this project will have paid back those modeling fees. Because we do a whole lot more projects as engineers than HOK does as architects, we had an even larger portfolio of projects to look at. So these are projects from TLC, where we looked at, once again, what was the fee for energy modeling, and then how much energy savings was realized from that modeling exercise. Once again, seeing that for projects of any size at all, the payback on those fees was less than 6 months. So being an engineer, I had to graph and do a curve fit of this data, and you can see that on the horizontal axis is project area. So small projects at the left end of the graph, really large projects on the right side of the graph, and then the simple payback in months is the vertical axis. And once you get below about 20,000 square feet, the overhead associated with doing an energy model is kind of takes over. And the paybacks get extended. They get over a year for really small projects. But for projects of any size at all, the fee is change that's lost in the couch cushions of the owner. If you go into the owner's office and take the couch cushions out, you'll find enough spare change to pay for the energy model on one of those major projects. So almost instantaneous payback. So don't tell me that an owner can't afford to pay for energy modeling, especially early energy modeling, because it doesn't take very much time at all. The more complicated the design gets later on in design, the more difficult the energy modeling process becomes. So that a compliance model or a lead model or a code compliance model, to do that is weeks sometimes of effort. To do models during conceptual and schematic design is hours. So if you can only do one or a few things, first, set yourself an energy use intensity goals. Second, set yourself some peak load goals. Third, look at doing some climate or program appropriate passive strategies. And then fourth, do your modeling. So Climate Consultant is, once again, a piece of freeware that will really help you with passive strategies and doing the climate and site analysis that we call for as being mandatory in the Ashrae Standard 209. And it's really good for small commercial buildings and residential buildings. The Ashrae Advanced Energy Design Guides are a set of prescriptive guides that, once again, if you can't afford to do an energy model, these can give you some of those goals toward designing toward, like a composite U value on your envelope, and lighting power densities, and HVAC load maximums. And then the 2030 palette that's put together by Ed Mazria's group, Architecture 2030, once again, is a collection of best practices that puts those best practices together for specific building types and locations. So you can really get a lot of good energy information without doing an energy model, especially on those smaller projects. So really quickly, I want to just show you what we at TLC do when we do a modeling cycle 3 analysis. So this is for a project, a hospital in the Tidewater area of Virginia. And so it's got a climate and site analysis. It did some conceptual design modeling and then did the load reduction modeling. This is information on the climate analysis, looked at what we were going to be doing in terms of evaluating a baseline versus proposed things that the architect wanted us to look at. This is how the energy use breaks down in that building. We looked at different energy consumption or energy conservation measures. That's what ECM stands for. And then created this cascade of showing how much energy was being either saved or lost by different what we thought were energy conservation measures. So this is an interesting one. In a hospital, if you reduce the lighting power density, sometimes you don't save energy, because in a hospital you need reheat because of the high air change rates. And we actually got into a situation where we reduced the lighting power, and the heat of the lights had to be made up by burning gas in the boiler. So sometimes an energy model will surprise you. This is a sensitivity analysis on glazing, where we looked at both annual energy and peak cooling loads for different U values and solar heat gain coefficients to help the architect evaluate different glazing selections. We looked at changing the insulation of the walls, both less than code and more than code, looking at both annual energy use and peak cooling tonnage, and then did some solar investigations to help the architect understand where solar loads were going to be great and where they were fairly minor. As you might guess, the north face and west face are a lot cooler than the south and the east faces. So that's that. It's time to move to some questions.
That was great. Thank you so much. I think this was perfectly titled Demystifying Energy Modeling. It was a really great presentation of, I think, resources and rules of thumb that we can adopt, but also where it's really important to bring in folks with deep knowledge of building science. And these are questions we've been batting around, and the clarity that you brought through this presentation is much, much appreciated, Kim.